Okay, so one thing I noticed reviewing my videos is that I fall back on Desmos a lot. Yeah, I know in a test you're going to have to use a calculator, but I assume from functions 11 that you've learned how to punch in f of 3 and figure out the equivalent y value or the f of 3 value, um, and are able to do basic subtraction, basic division. When I'm teaching this, I'm trying to show you how much faster you can learn using the tools available to you, and they're used as a backup. Same reason I just don't want you copying my answers to these videos. I want you um, to stop and then try one yourself. So you learn the method, try one yourself. If you make a mistake, watch it, then try again. Because nothing beats doing. Nothing. You will learn the fastest by doing these problems. So this is all about using rates of change to create a graphical model. And again, the application is that in science, you're either interpreting data from a graph or from data, or you're creating a graph or presentation from data. So in this case, a very common one, let's have a look at this, and I think I touched on this before. If I have a graph here, and along the x-axis I have time, let's say time in hours, right? So as I go along that graph this direction, and it's the independent variable because time often is, and it progresses in that direction. That's how I would read my graph always. And then along here, let's say I have distance in kilometers. Okay? Now, let's say I walk away from my house. Now, obviously I can't just do a straight line upwards because that implies that zero time has happened. If I draw a line like this, it's not very realistic because it implies zero time. It took me zero time to go from here to here distance away. And that's not true in any situation, so it's kind of odd to see that. Inversely, you could see a horizontal, which just means for this amount of time, I've not gone farther away from my house or closer to my house. So you can see a horizontal. But let's say you see a line like this. And let's say this line is f of x is equal to x. Let's just say it's a nice, consistent line. F of x is equal to x. What do the values mean? Well, obviously, the values along the x-axis are time, and along the y values are distance. So this graph, if I had labels here that said, 5, 10, and the same equivalent down here, 5, 10, and I could find some dots on the graph, let's say there, and there, even though my dots aren't quite accurate. And I could say, okay, well, it's going 5 there, and 10 there. And I could say, well, what's his speed here? Well, it's clear his speed is 1 for 1 because his delta y from 5 to 10 is 5, and his delta x from here to here is 5. And if you take 5 divided by 5, you get 1. But what is that rate of change? Well, the rate of change up here, that's the y, so that's the first thing we'll mention, 5 kilometers per 1 hour. And that's what it means. Suppose this had been 5 to 25 instead. 5 to 25, which means his rate of change up here would have been 20, his delta y, and his delta x would be 5. And if we take a delta y over delta x, and that's signified by that, change in, we get 20 over 5, and that comes out to 4. But what does that 4 mean? It means his rate of change is 4 kilometers per hour. Now notice that when we take the rate of change of a distance over time graph, we get speed. So that means we're getting the rate of change becomes a measurement of the slope of that line. So, and it just becomes a constant in this case, the constant number 4. Let's change this up a little bit. Take the similar graph, but instead of a straight line, let's take a parabola. So let's say he's going from at 10 kilometers, he's in 10 hours, but he's taking this kind of weird route to it. All right. And yeah, I didn't quite get that right, so let's try again. And taking that weird kind of parabolic route to it. And even that would be bent closer in, but let's just look at this. And we could see, okay, yeah, 10, 10 here. It's definitely a dot. But then when we go down to 5 here, we don't get 5. We get like 2.5. So it's clear, even from the graph, that he's getting, what's this look like? He's getting further in shorter amount of time. He's getting further in shorter amount of time at this place. So is he speeding up or slowing down? Well, he's speeding up, because if we were to take a look at his rate of change here, we would see he's traveled 2.5 kilometers in 5 hours, which is the same as half a kilometer, or 1 kilometer every 2 hours. If we look at his rate of change here, it's 10 divided by 10. He's gone 10 kilometers, and that, I know that's a total average rate of change from origin, is what I'm taking essentially. When I do this, when I take the actual coordinate and divide it, I'm finding the average rate of change to origin. So think about that. This 2, 2.5 here at this point represents the distance in y values from origin, and the distance from the distance in x values from origin, and the distance in y values of origin. That would be the average rate of change between this point and origin. So his average rate of change at this point was 1 kilometer per 2 hours, or half a kilometer an hour, 0.5 kilometers every 1 hour. His rate of change here was 10 kilometers from origin. Again, if I'm taking an average rate of change, 10 kilometers in 10 hours, his average rate of change is now 1 kilometers an hour. His speed has doubled. His average rate of change has doubled from here to here, which implies that he must have sped up, which is what this arcing curve is. Now, if you look at it just instinctively, and this is what they're trying to teach in this chapter, you should be able to see that he's speeding up, because the distance he covers in time from here to here, that's a shorter arrow than if I take an arrow and draw it from the same spot all the way up. So I know that's a triangle, but you get the idea. If I think I can switch it, doesn't matter. You can see that green triangle is much longer than that red triangle. So that means from this point to this point, this is how much y increased in this, which could still be constant speed unless earlier on the ratios were more identical. For instance, right here, you can see if I look at the same arrows before that point, this is my delta y, so that's my change in time. And this is my delta x, this is my change in distance. You can see my change in distance is much smaller than my change in time. So if I'm looking at distance per hour, which is the measurement of speed, and this is smaller and this one gets bigger, I'm obviously going slower. If distance goes up and time goes down, I'm obviously going to get a faster number. If you don't believe me, let's look at 2 kilometers, 2 hours. When I divide those up, I get 1. Let's half this and double that. 4 kilometers over 1 hour, I'm now going 4 kilometers an hour, 4 times faster. So it's clear that when I increase the top number and decrease the bottom, or keep it the same, I'm going to go faster. What about the reverse? What if I double the bottom and half the top? I'm now going 1/4 kilometer per hour. So that means when I increase the bottom unit in this case and decrease the top, I'm going slower. Well, we can see that the bottom number here is bigger than the top number is. But over here, if I go from this point to that point, the green arrow is much longer than the red arrow, which means my top value has gotten bigger, and my bottom value is pretty much the same as that. So if your top value in any fraction and the bottom fraction stays the same, if that increases, your total speed or ratio, your slope, is going to go up. So that's one way to look at it. But essentially, visually, if you can see that, oh, this curve is going higher up the y-axis than it is along the x-axis, then my slope is increasing. And in the case of distance over time, that means my speed is increasing. Okay, that's a long way to explain that, but that's pretty much what this chapter covers. Now let's look at the reverse. What if I have a graph like this? Let's say he goes to here, and it's something like that. What's going on this time? Is he speeding up or is he slowing down? Well, let's look at 2 spots. Let's look at from here. Okay, it's roughly 7 over, let's say, 1. He's going the average rate of change to origin. The average rate of change to origin. Let's try to use it in blue. From this spot to this spot is roughly 7 over 1, or 7 kilometers per hour. The average rate of change to this one, to origin, is roughly 10 kilometers over 10 hours. So in this one, he was going 7 kilometers an hour. And this one, he's going 1 kilometer an hour. Did he slow down or speed up? It's clear he's slowing down between this average rate of change and this average rate of change. And it's also clear that the slopes are going down. I should have pointed that up on the other one. The other one, the slopes are getting steeper. This one, the slopes are getting smaller. All right. What's another way to look at it? Well, if we look at our green arrow for this point, we can see our delta x is very small. And if we look at a red arrow, we can see our delta y is quite large relevant, which doesn't mean much until I take my second one. So my delta y on this one hasn't grown that much, but look how much my delta x has grown. It's grown a whole lot. They're almost equal, and they are equal because they're at 10, 10. So you can see that he must be slowing down if this was his increase in distance over a small amount of time, and this is his increase in distance over a small amount of time, which is the same thing as I did with the origin. But if you take the rate of change there, which is a measurement as we've determined of speed, we'll see a tangent line that's kind of flat like that, and a tangent line here that's very steep. So clearly, if we take the slope, we'll also be able to tell if he's speeding up or slowing down, because it's clear that this line is much steeper. This green line right here is much steeper than this green line. Let's reverse these curves, because it's easy to see when the curve is this way. What if you do a weird thing, and you take a curve like this, and you drag this part down? Is he speeding up, or is he slowing down? And obviously, we're talking about these are going to be negative slopes, right? That slope is pointing down, that slope is pointing down. So there's a hint there. And what is actually happening? He's 10 kilometers from the house, and 10 hours later, he's close to the house. But right in the beginning, you can see his distance has decreased a lot in a short amount of time. And over here, between this spot and this spot, his distance has only decreased a little bit over a long amount of time. So he's going quite fast here and quite slow here. Another way to look at it is if we take 10 and divide it by like 0.1 here, he's going 100 kilometers an hour at this rate of change, roughly from origin, on average rate of change. And from this point, he's only going 0.1 kilometers over 10 hours, very slow. His average rate of change at this point is very slow. Well, to get from a fast speed to a slow speed, he must be slowing down. And at first, you can see the steepness of the slope. He's getting he's going fast, he's going slower, and he's going slower. So in this case, he is slowing down. He's going faster in the beginning, and then time is starting to stretch out. It's very easy to misinterpret that. What about a curved upwards slope? What if I take a slope that's going like this? He starts here, let's say. He ends up here, but he's going like this. And I'm going to put the curve at the end instead. Okay. Well, you can do your slopes again, and you might be tempted to say, well, he's slowing down because the distance is getting closer. No, he's actually speeding up. If the slope is his speed here, that slope is quite fast. That slope is more steep, and this slope at this tangent point is much steeper. So if the slope represents his speed, he's going fairly slow here, he's going faster here and faster here. It's very easy to think of that as he's slowing down. He's actually speeding up. If you look at it, his distance over this period does not change much, but the time is lagging on, which means the distance is small and the time is big, which will create a low speed. If you look at this point, let's say this area right here, his time that passes is very small, but his distance decrease is very fast. So he really is gunning it right in this stretch. Maybe he's sprinting, maybe he's driving, but in this last 30 hour, he covers most of the distance. He covers 9 kilometers, and in this part here, he only traveled 1 kilometer closer to home. So he's speeding up. And it's interesting. So this means he's speeding up, and this means he's speeding up, and how you do it is you take the slope. Now, yeah, he's getting closer to the house. That's why it's a negative slope. But the slope is getting bigger. So even though that's just directional, the negative means he's coming towards the house. The positive means he's moving away from the house. But in both these cases, that slope is speeding up. In the other cases, those slopes you can see are steep at first as we move. You're always moving left to right on a graph. And then they get less steep. They're steep at first, and then they get less steep. And since the slope we've already determined is distance over time, if this is getting smaller, then his speed must be getting smaller. And that's a good way of saying it. If this is stays consistent and this is getting smaller, then the result's going to get smaller. If this is staying consistent and this is getting bigger, then this is going to get smaller. So it's called inversely proportionate. Inverse relationship. It has a direct relationship. Time or speed has a direct relationship with distance. In other words, if both go up, if distance goes up, speed goes up. And it has an inverse relationship. Speed has an inverse relationship with time, which makes sense since it's 1 over t. So that means as time goes up, speed goes down. And that's how all fractions work like that. That's how acceleration works too. Acceleration is speed over time. And if you think really fast, now you can see that acceleration is the slope of a speed versus time graph. That should be a t. But we'll skip that. My point is you want to see these relationships and what they mean. So if I told you this, Bob walks 5 kilometers away from his house in 3 hours. He stops for 2 hours. And then he runs all the way home, 5 kilometers, in 1 hour. Okay, well, let's look at the timelines. Let's say Bob left at 12 p.m. So from 12 p.m. to 3 p.m., he covered 5 kilometers. From 3 p.m. to 5 p.m., Bob went 0 kilometers. And then suddenly from 5 p.m., maybe he heard his parents calling him home. 5 p.m. to 6 p.m., he raced home. He got a phone call, said, you were supposed to be home an hour ago. You're grounded. And he races home. He does 5 kilometers. Let's just look at our speed calculations just based on that. For the first part of the graph, Bob is going 5 kilometers in 3 hours, which is roughly 1.66666 kilometers per hour. Okay. In the second part, Bob is going 0 kilometers in 2 hours. And I forgot to cut, 2 hours. But it doesn't matter how many hours. He's going 0 kilometers an hour. He's dead spot. On the last part, he's clearly going 5 kilometers in 1 hour, so he's going 5 kilometers an hour. Let's just now graph this. And remember, our graph is not speed. It's going to be distance over time. So if I have some numbers here, and I go 5, 4, 3, 2, 1, and I just lowered a bit, probably around there and around there. Okay. And along the bottom, I just go roughly the same. 1, 2, 3, 4, 5. And even they need another space because the horizontal space isn't matching the vertical. It always helps to keep your spaces the same between units. It's still a bit off. Okay, so we know he starts at home, called origin, and he's 5 kilometers away in 3 hours. And actually, I need more hour. I need another hour in here. I need 6, I think. So in 3 hours, he's 5 kilometers away. So boom, I'm going to put it right there, and I'm going to draw a line between origin there. So that would be this proportion of his trip. Okay. Then Bob stops for, how many hours does Bob stop? He stops for 2 hours, so that means from 3 to 5. Bob doesn't increase his distance at all. Okay, so that's this proportion of his trip. And what happens to Bob in the last hour? Well, Bob races home. So we find where he last was. And where's home? It happens to be exactly on the x-axis because that's 0 distance on the y-axis. And there you go. Now, let's look at the slopes. It's clear the slope, this one, is positive and fairly consistent. It's clear the slope on this one is 0, and it's clear the slope on this one is steeper than that one and negative. which matches 1.66 and 5. So this one clearly is 5, and this one clearly is 1.66. And it's negative because he's heading home. He's heading back to what you were measuring with. You don't need straight graphs. Imagine I have a pendulum. Imagine I have a pendulum. The pendulum is like a long stick with a weight on the end, and it's swinging back and forth. And I'm going to call the middle home. So the middle is where I call home. So as the pendulum comes to home, then it moves past away from home, then it comes back to home, then it moves past home, then it comes back to home, then it moves past home, and then it does this. What do you think that's going to look like as a graph? Well, let's try that. It moves away from home, it comes back to home, it moves away from home on the other side, it comes back to home, and so on. We have a sine curve. So we can see where distance over time of a pendulum is probably going to be mapped out like a sine curve. It's same with a wheel, a bicycle wheel. If I match the bottom of the bike here, and I call this starting point, as he goes around and around, you'd think a wheel would follow this weird shape. But if you think about it a bit, that's impossible. It implies he goes back in time. In reality, if I light this up, this wheel goes up and down and up and down. So a wheel is also a sine curve. We'll get more into that as well. But at any point in this sine curve, if I take the slope, I'm going to get his instantaneous velocity at that point. So he's not moving here. He's coming back home quickly, negative slope, and then he's moving away quickly on the other side, which is still negative slope. Then he's stopping, and then he's coming back, and he's doing it all day long. So you have to understand what this means. And if somebody says, what's the sharpest speed on this sine curve? You'd have to realize it's somewhere around here. The steepest slope. You might even say, oh, it's closer to here. Except you're going to notice that this is called an inflection point. In other words, it's the steepest here, and then after that point, it's getting less steep. And why is that? If you look at it carefully, I have no slope. I have a little negative slope. I have a big negative slope. Suddenly here I have less of a negative slope, and I have a flat slope again, which means at some point here it started changing its speed. It's called an inflection point. Remember it, inflection point. Then I have steep, steep, and then I get less and flatten again. So again, another inflection point, and we're going to work more with inflection points in this chapter. Not this chapter, in this course. A lot of talk, and you can skip and play 2 times speed. But let's look at some of these graphs. So it's clear he's moving quite quickly here because the slope is steep, and he's moving away from whatever he started at. In this case, it was he walking to work. Then he stays at work from this time, which is about 3 o'clock, until 5 o'clock. That's a nice work term there, Steve. You work 2 hours and come home, probably get fired next week. And then he's walking slower home, probably because it's a nice day, or he stops and talks to people. Well, he doesn't really stop, but he takes a nice leisurely walk home. His speed here is faster. His speed here is 0. His speed here coming back is slower. And you can do delta y's at any time. You can take a slope. Since these are lines, they're going to be the same slope wherever you take the delta y. Not so for curves. Here we can see his distance is increasing. Oh, wait, this is a speed versus time. So we should look at it in those terms. He is going faster in speed in this last part, and I can tell because if I drew here, I'll show you. It's the same thing we just did. If I look at the coverage of time here versus the coverage of distance here, it's clear he's covering more distance in a shorter amount of time at this stage of the graph than he is here, which means he is speeding up. And you might say, well, he stopped here, which would be true if it was distance over time. But that just means his speed, if I look at the units, if I call these units of 2, 4, 6, 8, 10, his speed is 10 per whatever time. His speed is consistent. In other words, he's got the gas. So what's going on here? Well, he's probably getting on a highway. He's accelerating to get on the highway, then he's keeping a consistent speed of whatever this is here, and then suddenly jams on the brake and then speeds up. Now, it's very easy to think of this as speeding up, right? And actually, I just said speeding up, which is not correct. But if you look here, he's decreasing his speed a lot in a short amount of time, taking an average rate of change between those points. And then at this triangle, I can see he's decreasing his speed slowly compared to the time that passes. So he's actually decelerating quickly, and then he's doing a little less here. And you can see that directly from taking tangent slopes. His instantaneous tangent slope, or speed, at any point is, and actually that tangent point isn't speed anymore, and I'll get into it. What would happen is if we took a triangle, like we're taking a slope, well, we're taking delta y, which is speed, over delta x, which is time. And what's the definition of speed over time? It's not speed anymore. It's acceleration. It's acceleration. Acceleration, you'll learn from physics, is speed over time. So now if we take the slope at any one point, we're not getting speed, we're getting his acceleration. So I can see he's decelerating here. Why decelerating? Decelerating quickly because it's negative slope. And then he's not decelerating as much here. He's accelerating. Why accelerating? Because it's positive slope here. So he's getting on a highway, and then he's decelerating. Now you might say, how is this relevant to where he is from his home? And you're right, it no longer measures, this x-axis no longer measures his distance from the home. It just measures how fast his car is going. So if you look, he's starting at like, let's say this is 5, 10, 15. Let's say everything is 10, 30, 40. He starts at 5 kilometers an hour, and in a space of 3 minutes, he speeds up to 50 kilometers an hour, or miles per hour, whatever you want, per minute actually. So he's really accelerating. Then he keeps a consistent speed here of 50. And you might say, yeah, but his slope is 0. Yeah, you're right. The slope is acceleration. He's not accelerating, which means his speed is staying the same. And then he is quickly going from 50 right down to here to 20 in the space of like 1 minute. 50 to 20 in 1 minute. So he's applying more pressure to the brake. And then from here, from 6 to 10, the average, if I was to do a slope triangle, he's covering 20 kilometers per hour in 4 minutes. So he's decelerating 5 kilometers per minute squared. Why per minute squared? Because I'm taking his speed. I'm taking his speed, which was 20 kilometers per hour, and I'm dividing it by his time, which was 4 minutes. And actually, I should say, let's say meters. Keep it in the same units. 20 meters per minute, and I divide it by his 4 minutes, and I'm getting after I divide that 5, and what's meters divided by minutes divided by minutes? It's the same as meters divided by minutes times 1 over minutes. So how meters per minute divided by minute. And this is where you go back to your fractions. If I am taking meters per minute, that's his speed, and then I'm dividing it by minutes, okay? These are a fraction up here. This is a fraction, meters per minute, being divided by minutes. And minutes is not a fraction, it's minutes over 1. How do you divide two fractions? You multiply it. Instead, you get rid of that, and you multiply the reciprocal of the bottom. So it's being multiplied by 1 over minute. Weird way to think of it. What's 1 times meters? Meters. What's minute times minute? Meters. Minutes squared. So you can see that 5 meters per minute squared is a measurement of acceleration, which is why you'll hear in physics class that the gravitational pull of the Earth is 9.8 meters per second squared. Meters per second squared. Because it's a measure of the speed, which is already per minute or per second, divided by time again. So you get 2 time divisions. Tough to grasp. You'll get there. Just that's why units are important. All right, so then the book goes through and it shows these flasks, these flasks, these flasks. Imagine this flask full and you poured it out. It's the same shape throughout, so pouring it out is going to empty consistently. Same with this one. But if I'm filling up or I'm measuring the volume as it fills up, it's clear in this one that there's way more volume at the bottom and far less volume at the top. Whereas this one, it's continuously volume of this circle and continuously volume of circle. And actually the volume measurements for these objects are pi r squared, which is the area of a circle, times the height. That's exactly how you measure the volume of those things. Whereas this one, the circle's getting smaller and smaller and smaller. So you'd have to find the rate of change between this small circle down here and this big circle down here to find out the total volume of this flask. But this last part is exactly like the cylinder here. It's just the area of the circle here times this little bit of height here. So they ask, the rate at which the water flows from the tap is the same, filling all three containers. And then they show the graduated cylinder is filled consistently. The beaker is filled consistently, but the flask clearly has got that curve as the circle gets smaller, and then it's consistent for the last neck. Which means the water level, as I fill this flask, seems to go up higher faster than these two objects. But that's just because this little circle area is getting smaller and smaller. A cyclist is moving at a speed of 10 meters per second. She begins to slow down at the constant rate, and 4 seconds later is at the speed of 5 meters per second, which means she decelerated from 10 to 5 in 4 seconds. She continues to slow down at a different rate of speed and finally comes to a stop 6 seconds later. Okay, so sketch the graph. So here they do. Her speed starts at 10. 5 seconds, for the 4 seconds later, she's consistently decelerating to 5. And they did that because they knew she started from 10 and ended up for 5. And they just drew a straight line. And then from 5 all the way to the bottom, which is 0, it doesn't represent home anymore. It represents 0 speed. They just drew a straight line. Which means the rate of change here, she's clearly decelerating faster in this first stretch because the slope is steeper. And then she's decelerating a little bit slower in the last stretch. And you can find the slopes of either of those lines to determine her deceleration. So they find the average rate of change for the first one, and they discover it's 1.25 meters per second squared. And then the second line, they find the slope of they find the formula for the line, and they discover that the slope is minus 4 over 3. And therefore, her average rate of change is negative 1 point. Then they do it for, what was part C? Oh, they're estimating at 3 seconds. So they find the slope, and they determine that the slope is the instantaneous rate of change, and they would be correct. And the reason for that is when you take a tangent of a straight line, it's the same as the slope of the line. Using reasoning to analyze the situation. So Adam and his friends are standing still in front of a motion detector. Adam stands 5 meters in front and then walks 4 meters away at a constant rate of 10 for 10 seconds. So he's going at constant speed or a constant rate. Next, Adam walks 1 meter towards the center for 5 seconds and then waits there for another 5 seconds. So you can see Adam starts 0.5 away and he's walking away at a constant rate until he's 5 meters away. Then he quickly turns around, comes back, but then stands still. And the reason I can say this is because this is a measurement of distance on the y now. And this is a measurement of time. And the nice thing about that is since you know the distance at a certain time, you can just draw the dots and connect the lines. Because it says he's moving at a constant rate of speed, which means a line. A line is a constant rate of speed. And then if they ask instantaneous slopes, if you're dealing with a line, it's going to be the same as the slope of the line. But you just find essentially the slope of that line. And then the average rate of change between two distances is what we've been doing all the time. But the negative helps you understand if he's moving towards the sensor or away. If it's negative, he's moving towards. And if it's positive, he's moving away. And then the instantaneous rate of change for these things, you'll notice, is the same as the average rate, simply because we're dealing with a line. Then they mapped out his speed. And this is interesting. You might say, why does it look like that? Well, because his speed was constant here, and then he stopped. He had no speed. So that means he had this speed here, he had this speed here for that next time interval, and then he has zero speed here because he stopped. So they're just trying to teach you connection with physics and graphs and how to measure graphs. And then they also go through what I went through, which one is decelerating, and they go through how you can remember it. Then they ask you to do a few. Connect description with the image. Okay. All right, let's look at these. First of all, they distance. Yep, each one is distance over time. Important, always check your measurements. What's going on? Well, it's clear his distance is increasing with his time. Since, let's call this home, he's moving away. So his distance is increasing with time. Is that A? No. Is there no change? No. There we go. So C is there. In red, it's clear that he's farther away at this time period and closer here. So that means he's got a negative slope. If he's coming towards home, remember I said his thing will be negative. So his distance is decreasing as his time increases. His distance is decreasing over time, which, since time always increases over time, is what they mean, which means this one belongs to that one. Notice his distance stays the same no matter what the time happens. There is no change in distance over time. It's clear that this one matches that one. Which of the graphs in question one show that the speed is constant? That's a constant speed, that's a constant speed, and technically that's a constant speed. So they're all constant speeds. And that's because they're straight lines. So distance over time is the same no matter where I take the slope on these lines. And you might say, well, that's not a constant speed. But yeah, zero distance divided by 10 seconds is still 0 meters per second. It's still a speed. Jan stands 5 meters away from motion sensor. She walks 4 meters away at a constant speed, so a straight line, for 5 seconds. Then she walks 2 meters away from the location where she changed direction at a variable rate for the next 3 seconds. So she kind of moves away quickly, then slows down, and quick. She stops and waits at this location for 2 seconds. Draw a distance versus time graph to show Dan's motion. Now, they didn't tell us the variable rate. They didn't tell us if she consistently sped up and slowed down. But I guess that gives you total leeway to do whatever you want. So they'll probably say in the book multiple options, but here's one. So if I'm going to do an XY or an XY and just put like time, so we can see 0. Let's just do every 5. Oh, I got to do a bit more. 1, 2, 3, 4, 5. They're not spaced out correctly. 6, 7, 8, 9, 10. And then up here, I can just do how far does she go? She's at least 5. Let's just go like 8, 7, 6. Let's go 10 here and 5 here. So she's standing 5 meters away to start, which is nice, which means she's right here. And then she walks 4 meters towards at a constant rate for 5 seconds. So that means at 5 seconds she's 1 meter away because she walked 5 meters before. So for the first leg of the journey, we get to draw those 2 points. And because it's a constant rate, we get to draw a straight line. She changes directions. No, hang on. Then she walks 2 meters away from that location where she changed directions at a variable rate for the next 3 seconds. So we only know for the next 3 seconds she could do anything. She could do this, she could do that, but she's walking away, so it's never going to come back. So let's just say from 8, and she only walks 2 meters away, so from 1 to 2 is going to be 3. And we'll just say she's doing a slow acceleration. So we'll say it like that. And just like that. There. So she's definitely moving away the whole time because the slope is always like this. and she ends up here. 8 seconds. She ends up 4 meters away. 3 meters away. So that spot there is 3, 8. This spot here is 1, 5. And the original spot is 0, 5. And draw distance graph show. Okay, so this is the only spot that we don't have enough information. The variable rate can mean anything. It doesn't say she accelerates. Oh, then she stops at this location for 2 seconds. So she does not do anything for 2 seconds. So from 8 seconds to 10 seconds. So her spot ends up being here. It was 8, 3. I had it backwards. Ends up being 10, 3 because her distance didn't change. So the only mystery is this part, is how was her variable rate. We could have also done like a curve this way, in which she quickly walked and then slowed down. The only thing we couldn't do is a straight line, because it's a variable rate. You can see there's a lot of leeways in that. Rachel climbed Mount Fuji in Japan. There are 10 levels to the mountain. She was able to drive to level 5, where she began her climb. She walked at a constant rate for 40 minutes, so straight line from level 5 to level 6. She slowed down slightly and then continued at a constant rate. But then still had a constant rate, so a straight line for 90 more minutes from level 6 to level 7. She decided to eat and rest there, so she stopped, increasing her distance, so flat line, which took 2 hours. From level 8, she took 40 minutes. She traveled constant rate. So they're all connecting straight lines. 9, continuing on to 9 levels, she went a little bit slower. And you can even see if she took 40 minutes between level 7 and 8, and they're the same distances between 7 and 8 and 8 and 9, she took longer to get from 8 to 9, which means she walked slower. Whereas here, 40 minutes was the same speed here and here. Here, she took much longer between levels in 6 and 7, which means she's going slower. During most of the 1 hour she took to reach level 10, the top of Mount Fuji, she maintained a constant speed as she neared the top. However, as she neared the top, she accelerated. Using the information given in the following table, draw a graph time. So now they've converted levels 5, 6, 7 into meters. And you can see they're all 300 meters. No. So here, 7 and 8 is longer. So they kind of cheated in that these levels are not 300 meters apart. See, this last one's 340 and this last one's 400. If they were all the same amount of distance apart, then these times would indicate speed. But since they cheated me, you can forget what I said about speed, because since the distances changed, I won't know the speed till I calculate it. Calculator average speed. Now, interestingly enough, Desmos will let me do this, which is the table she gave. 5 was 2100. 6 was 2400. 7 was 2700. But that's not enough. We need to know the speeds. And I'm going to add another thing in here for a second. Was 3100. And finally 9 was 3400. And her last level she sped up right near the end, remember. So there's going to be a little whiplash, 3740. But what's interesting is this doesn't tell us anything. It tells us levels, but levels don't mean anything. So in terms of her speed, because the levels we need that speed in there. And we need this to go from 2,000 to 3,000 in steps of 1,000. There we go. So there she is. And this is level 5. So there she starts. And even if I connect these dots, which you can, let's see, there you go. You can see the speeds. And like I said, if these levels were all the same, that speed's a little faster. However, the levels are not the same. And what I should do instead is put it in terms of time. So she went from 0 here, and it took her 40 minutes. So that means here she was at 40 when she started this one. And that one took her 90 minutes. So I add 40 to 90. And I get 130 by the time she finished walking at 130. She stopped and she rested in there for a time period. For how long did she rest? Well, she rested 2 hours. 2 hours is 120. So I'm going to add 120 to the 130. And I get 250. And she stayed the same height. Right? She stopped there. Then you can see how the graph is going to change dramatically. Then from 7 to 8, it was 40 minutes more. So from 7 to 8, it was 40 minutes more. So that means when she started that, she ended it at 290. And then finally, and actually I'm not going to, because there's a 0 here. And then from 9 to 10, it was 45 minutes. So 45 minutes is 3:35. And then she took an hour, which is 60 minutes, to get to the top. And what is the top? So she didn't start at 2100. That 2100 should be down below. So I have to move all my distances up 1 because she started at an elevation of just below 2100. And it doesn't really matter what it was. And I got 2 of the same in there. 2400. Well, actually, no, that works. I just did 2100 twice. That's all. Let's see. So from 0 to that height, yeah, that should be less than that. So she started at level 5. Yeah, so she started at 2100. So it makes sense that this would end there. So she started there. 40 minutes later, she was at this one. For 90 minutes, she did the next one. So she ended there. So 90 minutes, I got it. Yeah. And she started there and ended at 2400. She did 2700. Yeah, so long as I keep adding correctly to the heights. So this is 3100 here. So that was 90 minutes. Then she stopped for 120 minutes. Oh, that's why it was the same. Stupid me. I forgot her stop. And then she took 40 minutes for the next height from 7 to 8. Yeah, got it. And then she did yeah, there's one of the mistakes there. It's 3100. And then she did the 45 minutes to get to 3400. And that's the last one. So she took roughly an hour, but she sped up in the last one. So 395 to get to her max height at the top, 3740. Now we're going to go home and see what we can see. And obviously I want to start from 0 here to 400 in steps of, I don't know, 50. And on the y-axis, I want to go from 2,000 to 4,000 in steps of 1,000. It's fine. There. You can see this one here looks like the steepest part. And notice how different this graph is compared to the graph I did before. Because now we have the distance between the peaks. She's really gunning it here. And technically, these last couple minutes, I should have like a curve. But I'm not going to have it. So really, if you were going to do this properly, in this last little stretch here, you just like account for a little bit here. You would zoom in. and you would try to represent it with an acceleration, like she's gunning it from here to the peak, and she's wherever the, you'd add some room there, and you'd put a little curve in there. There. You'd show that her last little stretch, she's really accelerating. Now, obviously, it wouldn't be that noticeable. All right. Calculate her average speed over each part of the chip. Draw a speed versus time graph. So we did the second part. So to do the average speed, you would just take your rate of change between these two values. So if you want, on Desmos, you could let Desmos do it, and you can just say what's 2400 minus 2100 divided by 40 minus 0. So her rate of change is 7.5 meters per minute. And then you can just keep doing that. You can just let Desmos do it. But keep in mind that you've got to get the distance between the peaks and the difference between the times. So slow down. And then obviously this one is 0 divided by whatever. You can just put whatever. It's 0. And then this stretch here, 3100 minus 2700. And we'll just skip this one. 3100 minus 2700 divided by the time, which is 40 difference. 290 to 250 to 290. 3400 minus 3100 is 300 divided by 335 minus 290, 45. And the last little bit's hard to estimate, but it's 340 divided by 60. So, which number is bigger? As surprisingly, this number is. So unless oh no, there we go, right there. So it's the 3100, 2700 and 3100 right here, just before she takes her, just after her break, when she guns it. Yeah, so it is indeed, this is going 10. That part going 10 right there. You can also always, this is the exact slope, but if your teacher only gave you the graph, you could simply do what we always do, which is draw a triangle and figure out the delta y, delta x. But the numbers are always going to give you much more accurate. Right? That's essentially what you're doing for all slopes. And this is just helping you understand draw a graph. So let's look at this. So they're trying to say the water level, which is how visually you would see the container being filled as it's being filled, right? So it's clear, other than the little slightly narrow part, this would be fairly consistent till it gets to about this curve. See this curve? Then it's going to seem to fill up fast. So you might see, even with this bottom part a little narrow, you might see a gentle curve at the bottom, then a straight line, then a gentle curve at the end. And it would look something more like this. Probably consistent. Then a straight line. And then another curve at the end. And the curves would be sharper depending on how narrow it gets at the top. Now look at this one. It's a small circle to fill here, then a bigger circle and a bigger circle and a bigger circle. So you're going to see the level like that. Since this is a measure of level over time, the level is going to seem to rise quickly, and then it's going to slow down, especially in the thickest part. It's going to be the slowest part. And then as it gets narrow again, you're going to see a curve. And then it gets wide again, you're going to see a slowdown. So you're going to see this interesting curvy, slowdown, curvy. But notice it's pretty much curved everywhere, which means your whole graph is going to be curved. So since it's narrow at the bottom first, you're going to see quite an increase, and then it's going to slow down. Then as it gets fatter, that's going to be the pretty consistent there. But then it's going to wrong curve. Then it's going to be accelerate quickly again in this last stretch. And then it's going to curve down again. It's going to do this weird thing again. So you can see this weird thing, and probably this last bit probably doesn't go on as long. But you will see it like that. And obviously the volume up here is a lot less than the volume up here, so it's going to have a much longer period going on there. All right, let's go to the next part. John is riding a bicycle at a constant cruising speed, so we're going to have speed on the y-axis. He slows down as he climbs a hill. At the top of the hill, he speeds back up, back to his constant cruising speed on a flat road. He then accelerates down the hill. And I guess down the hill would count as, no, he's not decelerating. Comes to another hill and coasts to a stop as he starts to climb. Coasts to a stop. So keep in mind on speed versus time, stopping is the only time the speed becomes 0. So if you're going to look at that, try to think of it this way. Always look at the speed as the y-axis so that you don't make a mistake. So I'm going to draw it like this. And he's riding at a constant cruising speed, which means he's, let's say, he's 5 kilometers per hour. You might be tempted to draw it like that because it says constant. But since he does not change his speed at 5 kilometers an hour, it is actually going to be like this. And since the bottom represents time, time's just going to click on consistently. And since his speed doesn't change, it's going to be like that. Then he slows down. So that means his speed is going to go down. What's down? Speed, it's down there. So that means from here to here, he's probably going to slow down based on the toughness of the hill. So you're probably going to have a curve. And it looks like he's slowing down less, as he's probably going to be this way, actually. Because as he hits the top of that hill, it's going to get harder and harder. So speed is going to decrease quite a bit versus time as he hits the steep part of the hill. At the top of the hill, he speeds back up, back to his constant cruising speed. Very good. This part's going to be tricky. There's his constant cruising speed. And to be fair, this bottom part should look more like this. It should look more like dipping down and then coming back up. Because here the hill is getting him, and then here he's zipping down that hill. So the first little bit will be slow, and then he's really zipping. So he climbs to the top of the hill. At the top of the hill, he speeds back up to his cruising speed, which is 5 on a flat road. He then accelerates down the hill. Okay, so that's the bottom of the hill, or the top of the hill. And then he's accelerating down the hill. Now, you might be tempted to go down because he's accelerating, but accelerating means he's increasing his speed. So this is the top of the hill here. Let's just represent it here. And then he's accelerating as he hits another hill. So here's his higher speed, so that's why he's accelerating. And he comes to another hill and coasts to a stop. So he comes to another hill and coasts to a stop. So you might be confused because you're thinking of a hill as up and down and up and down. And you're trying to bring him closer to the x-axis as he goes down the hill. Except that when he goes down the hill, his speed is increasing. So we can see his first hill going up it slowed him down, then down it sped up, and then he sped up going down another hill, then they say he cruised to a stop. Well, what's your speed when you stop? 0. So his graph will only go up and down based on his speed. So when he decelerates, it goes down. When he accelerates, it will go up. And acceleration is always going to be a curve. I mean, you could technically, you know what? You could probably do straight line, but it wouldn't be realistic, because that would imply he's consistently slowing down a little bit every second. Whereas we all know when we hit hills, we kind of slow down gradually. Sketch a possible graph of his elevation in relation to his starting point versus time. His elevation could be anything, because he's along a flat road. He slows down to climb a hill. He speeds up. He then accelerates down a hill, comes to another hill, goes to a stop. It all depends how high those hills are. So you can make up any elevation you want. I mean, one of those hills is definitely big because it stops them, right? Swimming pool is 50 meters long. Comey swims from one end to the pool to the other in 45 seconds, which means he swims from one to the end. He goes 50 meters in 45 seconds, which is a bit more than a meter a second. He rests for 10. Then he takes 55 seconds to swim back. So because he took 45 seconds first time, 55 seconds is longer. So he went slower coming back. Use the information to find the average speed for Comey's first length. So his first length is 50 meters divided by 45. So you just take your calculator and discover his speed. His average rate of change was 1.111 meters per second. What is the average speed for his second length? And I assume they mean from this spot. Well, his average speed is he covered 50 meters in 55 seconds. So he took him 0.9 meters per second, 909. If you were to graph Comey's distance versus time, so distance, not speed, for his first and second lengths, how would the two graphs compare? How is this related to Comey's speed? Well, the slopes of the graph, the slopes of the line would be related to speed. And one of them, since we're measuring a pool, if you assume the pool at one end is the starting point and call that 0 distance. So if we look at a pool and we just say, well, that thing there is, if this is our 0 distance and this is our 50 meters away distance, we would then draw a graph like this. We would find 0, 0 where he starts, and 50 is his distance, and it took him 45 seconds. So at 45 seconds at time, we would put a dot, and we would draw a straight line. Then it says he stops for how long? 10 seconds. So we do from 45 to 55, he stops. And then 55 to 110, he's slower. So the important thing is you would have to have a graph that is slower. And he comes back all the way to the other side. So he comes back to 0. So in this case, this is marking one end of the pool, this is marking the other end, and this is marking back to the beginning again. Since he comes back right to the beginning, he comes back to 0. This distance over time should be the length 55 seconds. This distance he rests should be 10 seconds. And this distance here should be 45 seconds, which means the slope of this line should be steeper than the slope of this one because he was faster here coming back. And if I were to take the slope, I'd get 1.09 of this one, and if I were to take the slope of this one, I'd get the 0.9, whatever we got. How's it related to his speed? Well, the slope is his speed. Draw distance versus time graph for can he swim. What is Comey's speed at time 50? Well, at time 50, he has been resting because 45 seconds he finished, and he's in that from 45 to 55 he's resting. So his speed is 0. Draw speed versus time graph for Comey's swim. Okay, that's very good. We would then draw this out. What's his speed in this first section? 1.09. So we would have a 1.09 on the y And he did it for 45 seconds, so we'd have a flat line. Then when he stops, right, his speed is 0. So for the next second, we'd have a line like this for his speed is 0. Then for his last leg, over 55 seconds, his speed is 0.9. So it would be a little bit lower than that first leg, and it would be flat. Why is it flat? Because his speed over that time was the same, and his speed over this time was the same. And that's his rest where he had 0 speed. Because now we're doing speed on this y-axis and time on this. So speed is constant because he was doing constant speed. Even here is constant speed. All right. The following graph shows speed versus time. Match each graph with the description below. Easy enough. I might have to stop, by the way. I'm going to try to finish this section, though, because it's really, they're just trying to get you used to physics. Okay, let's describe the graph before we go to description. His speed is not increasing much compared to his time in the beginning. Then his speed is increasing as his time goes on. So that means his speed is increasing. He's accelerating as time passes. The rate at which the speed increases is increasing as time increases. So that could be that one. The rate of speed decreases. No. The rate of speed at which increases is decreasing. No. The rate of speed decreases is increasing. No. So in this case, his speed is here. It's a little bit higher, and it's a little bit higher. So his speed is increasing. The rate at which his speed increases is increasing as time increases. So I'd say A is that one. What's going on here? He's slowly decreasing, and his speed is decreasing faster as time goes by. The rate at which the speed decreases is decreasing. Yes, so his speed is decreasing faster as time goes on. So this one would be C. What's going on here? His speed is quite high. It is decreasing quickly at first, and then it's decreasing slowly. The rate at which the speed increases, no, it's not increasing. The rate at which the speed decreases is increasing. The rate at which it decreases is increasing. Ah, I got this one wrong. This one, the rate at which the speed decreases is increasing because the slope is steeper. So this goes with D. C, the rate at which the speed decreases is decreasing is this one because he's fast here and then his speed decreases. And the rate at which it decreases is decreasing. The rate at which this one decreases is increasing because the slope is getting bigger. So his decreasements are getting bigger. That's what this confusing wording sounds. Finally, this one's speed, rate at which he's increasing is decreasing as time goes on. The rate at which the speed increases is decreasing as time, because his rate of speed is big here, less here, and less here. So this last one, B goes with D, and D goes with C, C goes with B, and A goes with A. Very confusing wording. A jockey is a guy who rides a horse. Whenever the jockey has the horse accelerate or decrease, he does so at a non-constant rate. So you're going to give a curve if it's a distance. First slowly, then more quickly. The jockey begins by having the horse trot around the track at a constant rate. He then increases the rate to the canter, so he's increasing the hoof beats, and allows the horse to canter at a constant rate for several laps. Next, she slowly begins to decrease the speed of the horse to a trot. Speed versus time. Okay. So just telling us that whenever it happens, it's at a non-constant rate. And at first slowly and then decreases quickly. So it begins by having the horse trot around the track at a constant rate. So that would be a constant speed. So you're just going to see a flat line. She then increases the rate to the canter and allows the horse to canter at a constant speed, going faster. Then she slowly begins to decrease the speed of the horse to a trot and then to a walk. So it depends how many laps. You're going to see, this is an incredibly difficult thing to interpret because it's so weirdly worded and probably has no thing. But if speed starts at 0, boom, and then it increases to a constant speed for 1 lap, increases to a constant speed for 3 laps, which I assume is going to take longer, and then decreases, and again it's slow at first and then fast, slow at first and then fast. to a constant speed and then decreases to a stop, sort of thing. Decreases to a stop. These things are so open to interpretation, it's incredible. But the point is, they're trying to get you to learn how to, whether you're drawing this or drawing this when you decrease. Because this bottom one decreases quickly, then slows down. This one decreases slowly, then quickly slows down. This one decreases quickly and then decreases slowly. So they're trying to teach you to learn which graph to apply to a situation. So if I have a car that's accelerating, accelerating, it's like that. If I have a car that's accelerating slowly quickly at first and then slowly, it would be like that. If I have a car that's accelerating slowly at first and then quickly, then I gun it. It's like that. If I have a car that I'm decelerating quickly first and then slowly but still decelerating, if I have a car that I'm decelerating slowly first and then quickly, it's like that. And that's always because you got to look at how steep these slopes are. They're essentially trying to make you learn how to study the words and study the graphs. Describe how you would walk toward or away from the motion sensor directed. Give each this. Okay. So in this one, we're going from 5 meters to 2 meters in 3 seconds. We're moving towards the sensor. Then we're moving from 3 seconds to 6 seconds. We're moving from 2 meters to 5 meters again. So since this takes 4 seconds and this takes 3 seconds, the speed that I move towards the sensor is faster. I don't know why that popped in. And you determine the speed by taking the slope. This one, I'm moving towards the sensor for first 2 seconds, and then I stop for a second. Then I move quite quickly for the next 2 seconds, and then I turn around and walk away from 2 meters to 3.75 in 1 second. So that's a very quick walk away there. And I would just take the slope of those lines to figure out the speed. In this case, the speed's negative as I approach the sensor and positive as I move away. I'm not going to do it because it's cross-country runners training for marathon. So he's running at different speeds. His program also requires him to accelerate and decelerate at a constant rate. So that's that's going to be a perfect curve. Today he begins by jogging for 10 minutes at this rate, then spends 1 minute accelerating to 10 miles per hour. So he goes from 5 to 10 in 1 minute. He stays at this rate for 5 minutes. He then decelerates for 1 minute to a rate of 7. He stays at this rate for 30 minutes. Finally, to cool down, he decelerates for 2 minutes to 3, and then for the final 10 minutes, and then stops. You're going to have a weird thing here. It's going to be flat line for speed over and over and over again, whatever his speed is increasing to, and matches the time they describe. And then between each thing, you're going to have a perfect acceleration. It's not going to happen too fast or too slow at any given time. That's a bad one, but something like that. Oh, no, you get the idea. And then for the decelerations, which I didn't do well here, because that's not possible where I've drawn them. For the decelerations, you can go either way. You can go like that, or you can go like that. Actually, no, you would always go like this. They're always going to be up bumpies because they're decelerating at a constant rate. Like that until they finally stop, whatever it describes here. Now, I could go through and do all the times, but really, I find those questions so... Create a scenario that could be used to create either distance versus time or speed versus time. No. 2 women are running on the same track. One has just finished her workout and decelerating at first slowly and then more quickly. So confusing about how it's worded. The other one is just starting her workout and is accelerating. At first quickly and then more slowly. So her acceleration is fast at first and then slows down. And her deceleration is slow at first and then suddenly she comes to a stop. Use one graph to illustrate the rates of change. A graph displays changes in rate of speed versus time. The graph has straight lines from point to point. If the graph had been drawn to display changes in time distance versus time, how would it be different? Oh, that's very good. So this is a good example. The speed charts, as long as your speed is constant, you're going to get horizontal lines. And obviously, to join those horizontal lines, there has to be a deceleration. Now, you could have a total stop. I mean, I could be running at 5 and then just stop and go 0. But I mean, technically, there would still be a deceleration line in there somewhere like that. Because you don't really, it's not possible for me to suddenly freeze time and stop. But for deceleration, you get a slow deceleration, you get curves like this, depending on how much time I take to decelerate. For distance graphs, you're always going to see something that's going up and down in slopey straight lines. The only time you're going to see curved distances is if I am accelerating. So my distance is increasing over different rates of time. But generally, for distance time where the person's keeping constant speeds, it's going to look like that. If I do acceleration in my speed versus time, I'm going to have curves. If I do acceleration in distance versus time, I'm also going to have curves. So, and as for the women running thing, I mean, I think they're saying one starts at fast and one's just starting. So this one that's starting is going like up here and then doing that and then constant speed. The other one decelerates slowly and then quickly, and the other one accelerates slowly and then quickly. So you're going to see a weird thing like that. I could bother with that, but really, I think I got my point across about this chapter. It's how to interpret. They're trying to get you used to physics and the difference between distance versus time and speed versus time. I'm sorry if I didn't completely answer some of these. I mean, if you want me to, say so in the comments.